And then if you're far from all of them, that means that the example does not belong to any class. So the process of fitting, so the process of deciding, well, what is the probability of the example being an outlier is done through a Weibull distribution. So the first step is to get these mean values, to obtain these mean values, and then fit a Weibull distribution using the, trying to estimate the maximum possible distance, okay? So you will fit this curve using all your known examples. And the equation for that is, you guys don't have the paper there, but okay, so here's the algorithm is, well, the algorithm is very simple. So the algorithm is simple just because they use an open source library to do the fitting, which is this fit high. But very simply, if you have the activation vectors for each of the classes, and then for each correctly classified example, you calculate, you update the mean value, and then you fit your extreme value distribution. You fit it, and then you have 3 parameters. So one parameter is a shifting parameter for the data. That K is called it's the scaling. Is it scaling or shape? Okay. So K is the shape parameter. So it's going to dictate if this is going to be like that, if it's going to be like that, if it's going to be decaying exponential. And then there is the scale parameter. So it's going to be taller, smaller, or the extreme value is going to be more accentuated. Okay? And then you just run your fit high. The library is done in C, so this is supposed to be very, very efficient. And then you're trying to estimate for the maximum possible distance. Okay? This fit high, it makes sure that you fit better towards very distant values from the mean. So if you can't fit the distribution perfectly, it's going to try to fit better towards the high value.
What does better mean?
Huh?
What does better mean?
Better. So when you're fitting a distribution, so these, of course, these points are going to be very widely distributed. So when you're trying to calculate the distribution, you want it to be more. This is an iterative procedure. So it's not going to give you the exact shape of the distribution. It's going to give you an approximate distribution with these parameters. So it tries to fit the distribution better at the high values.
Like minimize square there from the points at high values.
I don't know exactly how it does it, but so you have distance from the mean. Yeah?
Yeah.
So if your distribution, let's say you want your cumulative density function to look something like that. So that is the probability of it being an outlier. If this is the right curve, the fit high is going to try to find the right, but depending on the parameters or on the optimization procedure, this might look something like that. Right? So what fit high does is it makes sure that it is closer to a real one up here. I haven't gone into how they do it, but that is the intuition behind it.
I think they just maximum likelihood fitting of our distribution.
Okay. Yeah. Okay. And then you have, so this is not a real machine learning step, it's just a fitting step. So it's learning the distribution of the data. And then you have a model for the data. Cool. And then comes the interesting part. So they make some interesting statements here. Like already here, they make some interesting statements. One is that the goal, so the main one is that the goal of this is not to determine correctly the training class, but just to determine if the class is something that looks like what was seen on training. Okay, that's a statement down there. And I think that's very interesting because then they don't assess their model in prediction accuracy, but more in rejection accuracy. So in the open set, how much can you, how robust the algorithm is against wrong examples. And then comes the OpenMax part, which is the interesting part. So once we learn these models, so we have the mean values, which we can say, well, which we have to say. And now you have also the models for each class. So you have mean value, you have row 1, which is those 3 parameters, row 2 and row 3. So you have your 3 models for for the outlier distribution. And now you're ready to do OpenMax. So the algorithm for OpenMax. Let's see if I can control it properly. Maybe not. Okay. So this is the algorithm for OpenMax, and it's about substituting the last layer. So the argument is that the softmax, it's trying to estimate the probability over the known classes. So it is normalized to 1 to resemble a probability density function, right? That is wrong, because if you also want to include other things, then the probability doesn't need to add to 1, it needs to add to a certain amount, and then when you add the other unknown classes, then it has to sum to 1. Okay? So you have the activation vector for your example. So for your example, you have your activation vector, which is going to be this, right? You have the mean values and the Weibull models. So you have that. And then you have alpha, the number of top classes that you want to check against. So this was designed with, it was an image classification library, so they had 1,000 classes. So they argue that you only need to take the top 10, for example, or the top 5. If you have 3 classes, you can just take the top 1 or take the top 3. It doesn't really matter. But let's assume for generality that you just want to compare with the top alpha classes. So that's another parameter for the OpenMax algorithm. And then it's when it gets tricky. They do some of these steps just to it seems like it's just so that it'll work. So first thing is calculate the Weibull of each of the classes. So this here is the Weibull cumulative cumulative mass function. This right here. And that is going to give you the distance from the mean, so the probability that the point is an outlier. Then they scale it according to the number of classes that they have, so nothing fancy there. And they assign a weight, a Weibull weight. So this is 1 minus the probability of being an outlier. So this is the scale probability of it being in the class. They revise the activation vector, so now it's no longer the. So this is not the softmax, this is this layer. So we're getting rid of softmax, okay? So you revise this activation vector by multiplying the top alpha classes, you multiply them by this revised weight, and the rest by 1. So the rest remain unchanged. You define this, what they call the pseudo activation, which is just the sum of all, so the remaining probability, right? So this gives you the probability of it being part of each class. This is giving you 1 minus our probability times VIX, so times that. So what they're doing is they are reconstructing the probability for that last class that they are adding. Oh yeah, sorry, they add an unknown class. So they're reconstructing the probability for that class. Okay? Yeah.
This VIX, is that is I was the class?
VI is the activation. So it's so you have this.
Yeah.
So you have V1. So that one here would be V1 of X, V2 of X, and so on until V.
No, I believe.
Yeah.
But now the activation, the index is